What is the maximum safe operating temperature for BYOI rocket team's rocket if pseudo-staged? Our project was to analyze whether or not pseudo-staging the rocket team's motor would cause catastrophic failure due to heat transfer in the aluminum motor casing. Pseudo-staging involves burning sets of 2 to 3 fuel grains at a time in a motor that contains 4 to 9 fuel grains without separating the motor. In this setup, 2 grains of fuel have been fully burned, and 2 more grains of fuel are now being burned. These fuel grains can be seen as gray cylinders within the aluminum motor casing. Since the first 2 grains of fuel have been fully burned, the aluminum motor casing is exposed to the hot gases. A phenolic liner is applied to the interior of the casing to reduce heat transfer. This liner can be seen as black on the interior of the motor casing. Without pseudo-staging, the maximum altitude the rocket can reach is limited to around 10,000 feet without increasing the diameter of the rocket. Pseudo-staging, if successfully implemented, would enable the rocket to reach 30,000 feet without increasing its diameter. Thus, it is essential to ensure that pseudo-staging is possible and safe to implement. To understand the reasonable limits of the aluminum in the motor casing, this graph from ResearchGate was extrapolated using a cubic spline to determine the maximum safe operating temperature. Temperature affects the yield strength of metals, decreasing it with increasing temperatures. The maximum stress that will be experienced by the aluminum casing is 61.56 megapascals. The temperature at which the yield strength of the aluminum is 61.56 megapascals is 682 Kelvin, making this the maximum safe operating temperature. The rocket was simplified to a pipe with hot air flowing within and atmospheric air flowing outside. There are hot flowing gases from the exhaust of the burning fuel grains within the motor that are making contact with the phenolic liner, as seen in black, and cool atmospheric air flowing over the outside of the motor, making contact with the aluminum, as seen in a dark gray on the exterior of the cylinder. High temperature and high pressure gaseous rocket exhaust is difficult to find properties for, so air at 1 atmosphere and 3000 Kelvin was used to define the properties of the hot flowing gases. Only the aluminum casing that is in the section of the motor that is exposed to the hot gases is being considered in this project. It should be noted that the phenolic liner is not being considered to be an ablative material in this case, meaning that it will not melt. From Nusselt correlations, resistance methods, and internal pipe flow, the maximum temperature and time to maximum temperature were obtained. Nusselt correlations were used to find the convection coefficients inside and outside the motor. Internal pipe flow was used to find the average liner temperature. It was assumed that the liner temperature was constant along the length of the motor. A resistance network was used which included convection inside and outside the motor and conduction within the aluminum and liner. It was assumed that the heat loss was one-dimensional, with adiabats perpendicular to the flow direction. Transient analysis using the first term solution was used to estimate the time to reach the maximum temperature. Using the method described, the maximum aluminum casing temperature was 365.4 Kelvin, about 200 degrees Fahrenheit, reached after 46.41 microseconds, or 4.6 times 10 to the negative 6 seconds. The first section displays the heat transfer coefficients, resistances, heat transfer rate, mean out temperature of the hot flow as TMO, and the temperature of the liner exposed to the hot flow as TL. This temperature, as a note, is likely to ablate the phenolic liner. However, this will not be considered in this project. The film temperature, as seen at 332.3 Kelvin, was iterated on to find the exterior heat transfer coefficient. The second section displays the resistances for transient analysis, BO number, zeta 1, C1, and Fourier numbers. The BO number was greater than 0.1, indicating that a first-term solution would be necessary. The Fourier number was greater than 0.2, indicating that a first-term solution would be a good approximation. It is important to note that the transient solution used assumed that the walls of the motor casing were plane walls. This may have caused some error in the time to maximum temperature. To achieve a more accurate time estimate, a new partial differential equation would need to be solved for a hollow cylinder. The maximum temperature and stress experienced by the aluminum is within the predicted yield strength. Estimating that the maximum internal stress experienced by the aluminum casing to be 61.56 megapascals and a maximum operating temperature of 365.4 Kelvin, the yield strength is about 5 times larger than the expected stress. The temperature may seem low, but the phenolic liner is an excellent insulator, making this a reasonable maximum temperature. Additionally, if the motor got near the maximum safe temperature of 682 Kelvin, residual stress and tempering would occur with repeated use, making the motor unstable. Remaining well within the limit increases the lifespan of the motor casing. From the data collected, it was determined that the aluminum motor casing will not fail due to temperature increases from hot flowing gases. The next step to ensure the viability of pseudostaging will be to determine how long the phenolic liner can be exposed to high temperature gases before ablating. Another important step will be to determine the thickness of the solid fuel wafers that must be included to separate the stages. These wafers need to be sized such that they will not break up under pressure and clog the nozzle. They also need to be large enough to prevent upper stages from burning prematurely. One possible safety measure that can be implemented in case of overheating would be to include a set of screws of dissimilar metal attached to the nozzle at the end of the motor casing, so that before the aluminum casing yields catastrophically, the set screws will be destroyed and the nozzle will explode out the bottom of the casing, preventing the aluminum casing from exploding. For the scope of this project, the motor casing will not fail due to heat transfer.